Number 14. Now, number 14 has a lot of words, so you just need to pick out what it is they're asking and what information you need first. So it specifically says at the beginning that we are determining something indirectly by EDTA titration. So we have an indirect titration. We are using an excess of nickel, and the excess of nickel is then titrated with standard EDTA. So the tetracyanoniclate 2 does not react with the EDTA. What we have then, we have this treated with 25 milliliter standard solution excess nickel. Excess nickel required 10.1 milliliters. So that's where we're going to start. 10.1 milliliters of 0.0130 moles of EDTA, and that's per 1,000 milliliters for complete reaction. So the moles of EDTA, 1 mole of EDTA is going to be 1 mole of nickel, and this will give us how much excess nickel we had. So for the excess nickel, I get 1.313 times 10 to the negative 4, and that's moles nickel 2. So that is our excess. So now let's see what else we can figure out. In a separate experiment, 39.3 milliliters of this EDTA was required to react with 30 milliliters of the standard nickel solution. So we weren't initially given the concentration of our cyanide or our standard nickel solution. So we need to calculate it by using this information here. So we have 0.0393 liters of EDTA, and that EDTA has a concentration of 0.0130 moles per liter. And let's see, 1 mole of EDTA reacts with 1 mole of nickel, and we had 30 milliliters of it. So this will give me the moles, and I get 5.109 times 10 to the negative 4, and that's moles of nickel in this standard titration here, so we can figure out the concentration by then dividing that by the 30 milliliter sample, 0.03, because we need it in liters for molarity. So I get 0.01703, those are just all of the digits I get, capital M molar of nickel in the standard solution. So now we can go back to this 25 milliliters of this standard solution of excess nickel. So we know the concentration, we know the volume. I'm going to change my color here. So I can go 0.0250 capital L times 0.01703, and that's moles per liter, moles of nickel, not EDTA, moles of nickel. And this is the total moles that were added to the solution at the beginning. So I get 4.2575 times 10 to the negative 4. Again, that is moles of nickel. And this is the total moles. So my total nickel added will be equal to moles nickel complexed with Cn minus plus moles of nickel that were complexed with the EDTA. So the total nickel added, I'm just going to fill in what I already know, 4.2575 times 10 to the negative 4. Again, that's moles. The excess moles, so the moles that were complexed with the EDTA are here, 1.313 times 10 to the negative 4, again, moles of nickel. So now we can calculate the moles of nickel that complexed with the cyanide. I'm not sure why that's difficult. And I get that there were 2.9445 times 10 to the negative 4 moles of nickel that complexed with the cyanide. So now we need to look at our stoichiometry, because the question asked us for the molarity of the cyanide. So for every 1 mole or 4 moles of nickel react with 1 mole. Oh, I have that backwards. 1 mole of nickel reacts with 4 moles of cyanide. So I multiply this by 4 and get that there are 1.1778 times 10 to the negative 3 moles of cyanide. We were asked for the molarity, so then I'm going to divide that by 0.0127 capital L liters in order to get the molarity. And I get a molarity of 0.0927. And number 15, so we have a mixture of manganese, magnesium, and zinc. And we have a 25 milliliter sample. It's treated with 0.25 grams of hydroxyl ammonium chloride, which is a reducing agent, maintains manganese in the +2 state, 10 milliliters of ammonia, buffer with a pH of 10, Calmagite indicator diluted to 100 milliliters, warmed, titrated. We have a volume and a molarity, and then we have an amount of NaF. Liberated EDTA required 10.26 of this, 5 milliliters, aqueous displaced the zinc. Okay, so calculate the number of milligrams of each metal in the 25 milliliter sample of unknown. Where are we going to start? Well, let's start with how much EDTA was added, because our total EDTA will be equal to the EDTA that complexes the magnesium and the EDTA that complexes the zinc and the EDTA that complexes the manganese. So the total EDTA, we're going to start right here. So 0.03998 capital L liters times 0.04500 moles per liter. This is our total EDTA. And I get 1.7991 times 10 to the negative 3. Again, that is our total EDTA. So I'm going to put that right up here. So now what are we going to calculate? Well, we can calculate the moles that complexed with magnesium. Here, this is the part that I'm on. Let's see if I change my color to blue. So we're going to be using this. In order to find out how much EDTA was liberated when we displaced the magnesium. That's the EDTA that has complexed the magnesium. So I'm going to start 0.01026 liters of EDTA times 0.02065 moles per liter. Let's see, this is manganese. And that manganese, because what we need is the EDTA, 1 mole EDTA. But this is the EDTA that was liberated from the magnesium. So for the magnesium EDTA, I have 2.11. I'll give you all of the digits. 869 times 10 to the negative 4 moles. So now what about the zinc? I'm going to get rid of the blue over here. Where is the zinc? To displace the zinc, this time the liberated EDTA required 1547 of standard 0.02065 moles per liter. Now we are working on zinc. So perform this calculation. And I get 3.194. Again, I'm just going to give you all of my digits in my calculator. 555 times 10 to the negative 4, again, moles. So that's the EDTA that reacted with the zinc. So how many moles of EDTA reacted with the manganese then? Well, I start with my total, 1.7991 times 10 to the negative 3. And then I'm going to just subtract 2.11869 times 10 to the negative 4, and also subtract 3.194555 times 10 to the negative 4. So the EDTA, the moles of EDTA with the manganese is 1.26, and then I have a bunch of 7s, times 10 to the negative 3. That's a 3, not a 5. Again, that's moles. But that doesn't answer the question. The question is to calculate the number of milligrams of each metal in the sample of unknown. So we need to go to the periodic table and find the atomic mass. So magnesium is 24.35. Let's start there. 24.35. So because EDTA reacts 1 to 1, we know that 1 mole of EDTA will react with 1 mole of magnesium. Therefore, we have 2.11869 times 10 to the negative 4 moles of magnesium in this sample. So now all I have to do is convert those moles into grams by using the molar mass from the periodic table. Again, the periodic 305. I missed a 0, but it's the number at the bottom of these boxes that I'm looking at. 40. Now, you could use your dimensional analysis technique that in 1 gram there are 1,000 milligrams. The question does specifically ask for milligrams. So for this, I get 5.1, look for my sig figs, 5.149 is what I get, 49 milligrams, and that is magnesium. So now I need zinc. Zinc on the periodic table, zinc is a transition metal. 65.38 is the atomic mass. So I take my 3.194555 times 10 to the negative 4, and that is moles of zinc. Multiply that by 65.38 grams of zinc per mole. And then again, for dimensional analysis sake, in 1 gram, there are 1,000 milligrams. So for my zinc, again, 4 significant digits, and I get 20.89 milligrams of zinc were analyzed. And then similarly for the manganese, I have 1.26777755 times 10 to the minus 3rd, and that is moles of manganese. Go over to the periodic table, and I find my manganese right here. 54.938 is the value that I will use, 54.938 grams. And I get 69.6. I would round that up because I get 649. So I would round that to 65 milligrams of manganese. So that is, or those are, the masses of each of those metals in the sample of unknown that was analyzed.